6.7 Energy balance for closed system. In this section, we are going to talk about entropy production in a closed system. We learned that the entropy change of a system can be expressed as S2 minus S1 between the two states. Integral from state 1 to state 2, delta Q over T. And this is for internally reversible process. If there is no heat transfer to the closed system and the system undergoes a reversible process, the entropy change becomes zero. There are two ways that the entropy of a closed system increases. One is by heat transfer. The other one is by the irreversible process. So heat transfer accompanies entropy. Heat addition to the system increases the entropy. Heat rejection from the system decreases the entropy. So we can write the entropy change of a closed system in general form. So this is the general form of entropy change of a closed system. And this equation is called closed system entropy balance. And the unit of these terms is kilojoule per Kelvin. And this equation enables us to quantify the entropy production within the system. The first term, S2 minus S1, represent the entropy change between the two states. Entropy is a property. It is a point function. The second term, integral of delta Q over absolute temperature. The subscript B indicates the integrations is evaluated at the system boundary. Sigma is called entropy production or entropy generation. It is the entropy generated during a process. The entropy production is due to the irreversibilities occurring within the system. So it has the same unit as entropy, kilojoule per Kelvin, or on a unit mass basis, it's kilojoule per kilogram Kelvin. Entropy production is path dependent. The entropy production is not a property. The integral of delta Q over T represents the entropy change due to heat transfer. Heat is path dependent. It is not a property. Any real process always accompanies some degree of irreversibilities. So irreversibilities such as friction, heat transfer through a finite temperature difference, mixing gases, inelastic deformations, all these irreversibilities increase the entropy inside the system. So if the process is reversible, there is no entropy production. Sigma is zero. If the process is irreversible, entropy production is positive. But there is no way that sigma is negative. It is impossible to have a negative sigma. So the entropy productions is always greater than 0 or equal to 0. Sigma or the entropy production is considered as a measure of magnitude of irreversibility. The larger the entropy production, the higher the irreversibility of the process. In other words, the more inefficient the system. If the system produces work, the presence of irreversibilities will cause the work to be smaller. So we try to minimize the entropy production to have a more efficient system. Or if the system requires work, the presence of irreversibilities will cause the required work input to be larger. So we need to minimize the entropy production. Let's see an example. So water, initially a saturated liquid at 150 degrees Celsius, is contained within a piston cylinder assembly. The water undergoes a process to the corresponding saturated vapor state, during which the piston moves freely in the cylinder. There is no heat transfer with the surroundings. If the change of a state is brought about by the action of a paddle wheel, determine the net work per unit mass in kilojoule per kilogram and the amount of entropy produced per unit mass in kilojoule per kilogram Kelvin. So see the diagram. We're going to take the water in the piston cylinder device as the system. And this is a closed system. There is no mass crossing the system boundary. First, the net work per unit mass is to be determined. So we are going to apply the energy balance to the piston cylinder device. The piston cylinder system is stationary, so we neglect kinetic energy change, potential energy change. And the problem statements describe there is no heat transfer with the surrounding. So Q drops out. So the internal energy change of the system equals negative W. There are two types of work associated with the process: boundary work and paddle wheel work. The boundary work is done by the system, that is positive, and the paddle wheel work is done on the system, that is negative. Divide the equations by the mass. We arrange the equations. We can fix the states at the initial state and the final state. So see table A2. This is saturated water table. Temperature 150 degrees Celsius. The internal energy for saturated liquid. Internal energy for saturated vapor. So the net work is negative. This indicates the paddle wheel work is greater than the boundary work. And we are going to apply the entropy balance to the piston cylinder device. As the system goes through an adiabatic process, delta Q over T drops out. So the entropy change during the process is simply the difference between the entropy values at the final and initial state. Divide the equation by mass. lowercase s2 minus s1. This is the specific entropy. At 150 degrees Celsius, the entropy for saturated liquid, entropy for saturated vapor, are shown here. So the entropy change of water during the process is 4.9961 kilojoule per kilogram Kelvin. On a pressure-specific volume diagram, the area under the process is boundary work. But as the process involves two types of work, paddle wheel work and boundary work, so we don't have a defined path between the initial and final state. That is why it is represented as a dashed line. So the area under the line connecting two states is not work. Also, on a temperature entropy diagram, the area under the line connecting two states does not represent the amount of heat. It undergoes an adiabatic process. There is no heat transfer across the system boundary. Here is another example. Refrigerant 134A is compressed adiabatically in a piston cylinder assembly from saturated vapor at 10 degrees Fahrenheit to a final pressure of 120 pound-force per square inches. Determine the minimum theoretical work input required per unit mass of the refrigerant in BTU per pound. So we take the refrigerant as the system. It is a closed system as there is no mass transfer across the system boundary. And the piston cylinder device is stationary, so we neglect the kinetic and potential energy change during the process. At the initial stage, we know the temperature and the quality, so we can fix the state. At the final state, we know only one property, that is the pressure, 120 psi. So we need one more property to fix the state. And the minimum theoretical work input is to be determined. So we should note that the system will require the minimum work input when it goes through an internally reversible process. The process should not involve any irreversibility. So when it is an adiabatic and reversible process, the entropy change during the process is zero. It is an isentropic process. We can sketch the process on a temperature entropy diagram. State 1 is at saturated vapor phase. The isentropic process is represented as a vertical line. This is the isentropic process. This is a constant pressure line. The actual process will end up somewhere at the same pressure line, but with a higher entropy due to the irreversibilities. So this is the actual process. So this blue line is the actual process. You can tell entropy here is greater than the entropy at 2s position. We apply the energy balance to determine the minimum theoretical work. It is an adiabatic process. The system is stationary. Divide the equation by mass. At 10 degree Fahrenheit, the internal energy for saturated vapor is shown here. So U1 is 94.68 BTU per pound. At state 2, what we know is the pressure, 120 psi. We also know that it undergoes an isentropic process. So S2 equals S1. So S1 is 0.2214 BTU per pound degree Rankine. So see table A12E. At 120 pounds, we know the entropy at state 2, 0.2214, which is between these two numbers. So we need to determine the internal energy that corresponds to the entropy at state 2. So we do the interpolations between the two numbers. Internal energy at state 2 is determined 107.46. So we determine the minimum theoretical work. So this analysis enables us to set the minimum theoretical work using the isentropic process concept.